Okay, so now we're on to the ideal gas law. This is when we're not changing something about the gas, so we're not changing the pressure or anything. We're trying to find out more information about that one in particular gas. And again, this is called the ideal gas law because we're assuming that the gases are going to act perfectly, and we know just by being scientists that is not going to be perfect, but you have to just deal with that. This is an assumption. It works for like 97% of the time. But it's not perfect. So just keep in mind that. And our equation is PV equals nRT, and we should know that P is pressure, R is volume, N is moles, T is obviously temperature, and that's going to be in Kelvin. And then the last thing we're going to have is our gas constant, that R. And the gas constant is something that's just always in there that we just have to take into account when we do these problems. And we'll talk about which ones and all that kind of stuff. So just make sure you know PV equals nRT and you know what they mean. And if you remember from last year, sometimes we called it PIV-NERT. All right, so things to keep in mind. We just said it before. Temperature must be in Kelvin. And basically, remember, we are going to have to use R. It's a gas constant, and it's going to depend on what pressure we're using. So the pressure we're using or the pressure we want is going to dictate this. And you can notice there's two values of R. There's 0.0821 liters atmospheres over moles Kelvin, or you have 8.314 liters kilopascals over mole Kelvin. So clearly, we use the little one when we're using atmospheres, and we use the other one when we're using kPAs. If we're not in either of those, then we need to convert into one of them. And then again, this is an ideal gas law. This is not perfect. So just be aware that when we look at the next slide, no gas is perfect. It's going to be pretty close. So if you look here, we have an ideal gas on the left. The blue guy, he's going to take up 22.41 liters when he's 1 mole. And then the rest of them are actual real gases. So you can see they're very, very close, but they're not perfect. Although helium looks pretty rockin', pretty amazing. Okay, so what we're going to do is we're going to practice some pretty simple ones. And then we'll do 2 together. We'll have you do 1. And then we're going to say what else can we do with this, because there is some other things you can do with the ideal gas law. And gases aren't hard. We're not going to spend a lot of time on them. But you are expected to know them for the AP test, and they do really like them. Okay, first one, you want to read the problem. We're talking about calcium carbonate, it's decomposing, all that kind of good stuff. And we're making a gas, and they tell us we have a pressure, we have a temperature, and we have a volume. So, we're going to write down what we know. Our pressure is 1.3 atmospheres. Our volume is 250 milliliters, but we want that in liters. So we would divide that by 1,000, and we get 0.250 liters. And they tell us our temperature is 31 degrees Celsius, or 304.15 Kelvin. So the question is how many moles, and then from there, how many grams of CO2 are there? So we're not changing anything, so that's our giveaway. We're going to use PV equals nRT. So we're going to plug in 1.3 atmospheres, 0.250 liters. We don't know N. Now we have to pick the right R. And again, the R comes from what pressure we're using. We're using the atmospheres, so we need to use the R that has atmospheres in it, which is 0.0821 liters atmospheres over mole Kelvin. And then last but not least, we need our temperature, 304.15 Kelvin. So you do the math. We get 0.013 moles of CO2 gas generated. And then if we wanted grams, we would just multiply this times 44.0 grams per mole, since that's the molar mass of CO2. So the N is our moles. If we wanted that grams, we would go one step further. All right, next one. When you buy tennis balls and they're nice and bouncy, they have air and nitrogen in them, and they give us that nice bounce. What we want to know is basically what's the pressure inside the ball if we know this information. So first thing they tell us is our volume is 144 centimeters cubed, which is 144 milliliters, or 0.144 liters. And those are kind of general knowledge things that you should know. You should know centimeters cubed equals a milliliter. You should be able to go from milliliters to liters pretty simply. They tell us our temperature is 24 degrees Celsius. My marker would like me. Which is 297.15 Kelvin. And then last but not least, they tell us we have 0.33 grams of nitrogen gas. Well, we would want moles, so we're going to convert that. And 1 mole of nitrogen, N2, is 28 grams, which is 0.012 moles. So we have N, T, and V. Hopefully we're going to be solving for P. So we have PV and RT. So we don't know P. Plug in for V. We figured out what N is. We have to pick the right R again. And again, R depends on what pressure we want. If you look here, it's asking us for pressure. It doesn't tell us which pressure we need, so we can pick. So I'm just going to pick the one that gives us atmospheres. 0.0821. Again, liters, atmospheres, moles, Kelvin, over moles, Kelvin. I'm just running out of room. And then I'm going to multiply it by my 297.15 Kelvin. Solve for pressures, and look at that. Your tennis ball is twice your atmospheric pressure. So again, just using PV equals nRT, you just need to be able to read it. All right, next one, take a break, see if you can do them. Make sure you can do A and B. And then when you come back, I'll have the answers written up there for you. One thing you do need to know is 1 meter cubed equals 1,000 liters. That's the only thing that would be helpful. Okay, so here are your answers for both A and B. And basically what you're doing is you're seeing you have this storage of natural gas, and you have a really cold day, and then you basically have a really warm day, and we want to see, what's that telling us. So first one, it's a cold day in December. They tell you how big it is, and basically you want to know how much it is. So we have 2.2 atmospheres, 1,000 liters, and you solve for N, so there'd be 104 moles of that natural gas. And for letter B, we want to know the volume. So again, now we're saying we know the amount of moles, and we just plug in for our volume. All right, so what we're going to do now is say, what can we do with the ideal gas law that goes further? The next two you do not have in the AP thing. I won't give it to you for the stuff. So you need to make sure you have these because you can figure out the molar mass of something, and you can also figure out the density. So I'm going to derive it. You don't need to derive it, but you either need to memorize it or you need to be able to understand how you get it. So two things. You want to remember if PV equals nRT, and you want to remember that N is your mass. This is mass over big M, which is molar mass. So first thing I'm going to do is say, okay, I'm going to plug my moles in. So we're going to have little m RT over big M. And then basically what we want to do is solve for the big M. So MPV equals little m RT. So if I know everything about my gas, I can actually solve for my molar mass. And I could use this equation to get my molar mass. Again, you don't need to memorize the derivation, but you have to understand it. You have to be able to use it to do this. Same thing goes for density. And we're going to actually go from what we just had over PV. And just remember that density equals mass over volume. Well, if I look at this equation that I have mass and I have volume, and they're over each other. So if I pull mass over volume out, I can actually put density in, and then I can rearrange. To get my density of a gas. So you should be able to get your molar mass of a gas, and you should be able to get your density of a gas. Or if they give you your density, you should be able to actually solve for them. So you need to know both of those. You need to kind of just get used to them. Okay, so we're going to do 3 problems, just showing you how to use these, and then we're all done. So we have cyclopropane. It's a general anesthetic. We know its molar mass. We want its density. So again, clearly we're going to use the equation that gives us density. So we have density equals molar mass times pressure over RT. And if we look this up, we have 42 grams per mole. And they tell us it's 1.02 atmospheres, which means we need to pick the R with atmospheres in it. And that's a little one, 0.0821 liters atmosphere over moles Kelvin. And then we need our temperature in Kelvin, 25 degrees Celsius, turns into 298.15. The number is easy, we get 1.75, but the units you have to be careful about. So what I'm going to do is just write my units over here on the right, and then cancel everything out. So first thing you see is we have moles on top, moles on the bottom. There you go. We have atmospheres on top, atmospheres on the bottom. And then we have kelvins. We have on the bottom we have 1 over Kelvin times Kelvin, which leaves us grams over liters. And that would make sense for density. So you gotta be careful with your units. Gotta play with those math. All right, what I want you to do is try the next 2. What'll happen is we'll stop the video. When they start it back up, the answer is going to be there, totally written out. So make sure you can do it. So try the one with Saturn's moon. Make sure you can do the density. And then when you come back, the answer will be there. So here's your answer. You had to use the density equation. Had to make sure you read everything right. Obviously, it's really cold on Saturn's largest moon. And as a result, the atmosphere is really dense. It has a thing of 5.9 grams per liter, which is pretty dense for a gas. All right, last one you want to try today. So you want to calculate the average molar mass. Again, stop it, do the work. When we come back, the answer will be there. Okay, so here's the answer. The first thing you're going to notice is since they gave me density, I had to use the equation with density in it. But what you want to notice is I had to rearrange it to get what I wanted. So I had to first rearrange it for molar mass. The second thing I had to do is they gave me my pressure in torr. There is no R that has torr. So what I did is I had to convert torr to atmospheres first. So I divided it by 760 to get it into atmospheres first. You could have changed it into kPa and gotten the same answer. The important thing is you used the right equation, you plugged it in, and you got 29.0 grams per mole. So make sure you do this for homework. These aren't hard, but if you're not practicing them, the test can get pretty nasty.